Based on everything we've discussed so far, and assuming they proceed through an anti-periplanar transition state, try to predict the products for the following reactions. I will give you the answer that this is a C-type isomer. This one is going to be an E-type isomer, alkenes both. So I'd like for you to sort of work it out to see if you can get these. For the following substrate, this one right here, the beta carbon has two beta hydrogens. There are two different rotamers where a beta hydrogen is anti-periplanar to the leaving group, and so two stereoisomers will be formed. You have two possibilities. In this case, the reaction will be stereoselective, but not stereospecific. In other words, you will get both products, but one of them will be the preferred. It will show up in a much larger percentage. E2 elimination will be stereospecific only when both the alpha and beta carbons are stereocenters. There are many factors to consider to correctly predict the product of an E2 reaction and decide what the major product will be. Some of the questions that you need to ask yourself every time you're analyzing one of these systems is, will the substrate react stereospecifically, or will it be a stereoselective E2 reaction? Will the substrate produce several regioisomeric alkenes? And if so, what will be your major product, minor product, etc.? The only way to really get this down and to be able to answer things within a reasonable amount of time is to just practice. There's a ton of practice problems that we have available on our platform. I advise that you kind of work through them to see if you can rationalize the answers as you work through them. Now let's talk a little bit about unimolecular reactions. SN1, the one stands for unimolecular, and also E1 reactions. Consider the following reaction we have here. We have terbutyl bromide interacting with ethanol, forming a substitution and an elimination product. Now, the substrate is a tertiary alkyl halide, so SN2 reaction is just not going to happen. The reagent is ethanol, which is not a strong base, and so an E2 reaction is also unlikely to happen. Now, experimentally, if you carry out this reaction, you will notice that you end up with a first-order kinetics. In other words, the reaction rate will depend only on the substrate, so just the one species. What that means is that neither SN2 nor E2 reactions will take place. The mechanisms of substitution and elimination in this case both start with the same step, the formation of your carbocation, or the ionization of the substrate. In this case, as we remember, the arrow represents those electrons. The electrons are getting attached to that bromide, which then just leaves, right? That will be your leaving group, and you end up with a carbocation. After the carbocation is formed, it will either undergo substitution or elimination, depending on how it reacts with the solvent, in our case being ethanol. Let's go first through the substitution mechanism. The substitution reaction of a tertiary substrate in an alcohol solvent like ethanol proceeds through a two-step, consecutive two-step or stepwise mechanism. First, you have your leaving group gets lost, like we just saw. You have your carbocation, then ethanol, which is both your solvent and your nucleophile in this case, gets attached to the carbocation. You see that the lone pair from oxygen just getting attached. Afterwards, then you get a deprotonation. So technically, you have three steps, but we don't really consider too much the last step, that the proton transfer step, as part of the reaction mechanism. This is called a solvolysis because the nucleophile is also the solvent. If you use water as your solvent, then it becomes hydrolysis, which is a type of solvolysis. The highest energy transition state in SN1, we have the entire reaction diagram. You have three bumps, this one, and then lastly the deprotonation. The loss of your leaving group will be your highest energy point in the entire process, so the activation energy relies on that step. That will be your rate determining step. Since the formation of the carbocation requires only ionization of the substrate, the rate of its formation depends only on the substrate. So the reaction follows first order kinetics like we have mentioned before. So SN1, we kind of discussed already what this meant. S stands for substitution, N for nucleophile or nucleophilic. And in the case of SN2, it was the 2 stood for bimolecular. In this case, we have 1, so it's unimolecular. A substitution reaction that occurs stepwise, where the leaving group first leaves to form a carbocation intermediate, followed by a nucleophilic attack, is called an SN1 substitution. Remember that when the nucleophile is a neutral species, such as an alcohol, there will be a proton transfer after the nucleophilic attack. This is important when you're being asked what is the final product. Make sure that you remove that proton. Now let's look at the elimination. The elimination reaction of a tertiary substrate in an alcohol solvent like ethanol proceeds same way, stepwise mechanism. In this case, your ethanol, instead of acting as a solvent, it will act as a base to deprotonate the carbocation and form your alkene. Like SN1, the E1 mechanism is unimolecular and follows the same kinetics of first order. Because SN1 and E1 reactions proceed through a carbocation intermediate, the carbocation may rearrange from a 1,2 hydride or methide shift. So it may move a little bit, either a hydride, that's a hydrogen with a negative charge, or a methide, which is a methyl group, again with its own electrons, to form whatever is most stable in that step where it's a carbocation, and then proceed through the substitution or elimination. Now, something important to note is that regardless of whether you're pushing for a substitution or elimination, here in the example on the top, we're pushing for substitution, we're also going to get some of the elimination product. The same is true when you push for elimination, you get some of that substitution product as well. So in practical applications, we're talking about the experimentally, you have to have an isolation and a purification step after your synthesis. The better the leaving group, the faster the reaction proceeds, right? The idea here is that if you can get that formation of carbocation to happen as fast as possible, since that is the rate determining step, the faster you make that happen, then the faster the entirety of the reaction happens as well. So we have here we are comparing halides or alkyl halides, right? Fluoride being small, highly electronegative, and you keep moving through the periodic table in that column of the halogens. Iodine is much larger, so it actually allows for it to become a much more stable leaving group, so it is easier for it to just leave the alkyl halide, making it much more reactive towards this type of reaction. The more stable the carbocation intermediate, we sort of covered that already, the faster the SN1 and the E1 reactions will be. Solvolysis reactions of primary secondary alkyl halides are often too slow to observe the formation of SN1 and E1 products. However, for tertiary alkyl halides, as well as benzylic, like the one here, and allylic halides, they will undergo solvolysis at a practical rate. So these are actually very good for studying reaction kinetics. These two are actually great because they're resonance stabilized. Makes them a little bit longer lived than its counterparts, so they're actually very good to study. In general, a primary secondary alkyl halide will only undergo solvolysis if rearrangement to a more stable carbocation is possible. For tertiary species, allylic and benzylic alkyl halides, all of them will undergo solvolysis to give a mixture of SN1 and E1 products. Like we saw with E2 eliminations, it is possible for E1 elimination to yield more than one regioisomer, as in the following example. So we have an elimination here, and with eliminations, as you know, we're looking for those beta hydrogens. We have one here, here, and here. So those are the hydrogens in the beta carbon position. So when that happens, you may get an elimination where the substitution happens here, or you get one where it happens in either of these, which are equivalent. So that would be when you have an elimination there, then you get this product, When the eliminations happen through here, you get this product. And then you get a little bit of the substitution product. In E1 reactions, you'll always see that you get the most stable alkene as the major product, which will be the most substituted alkene. In other words, this will be your major product. So E1 reactions are regioselective, but we cannot control regioselectivity like we can with E2 reactions. It is further possible to obtain several alkene stereoisomers in an E1 reaction, just like in the reaction we see here. So you can see the major products. So we have beta carbons, beta hydrogens here, here, and here. So these two will be very similar. One of them will give you the E versus the Z isomers, which are these two right here. You can expect the more substituted in the transposition, the guy right here, to be the major product. And then you get the least substituted as your minor product. You're also going to get some substitution product. It still holds true that the E1 reaction will give the most stable alkene as the major product. When two stereoisomers are obtained, the least sterically hindered isomer will be more stable. When the alpha carbon in an SN1 reaction is chiral, then we obtain two substitution products that have opposite configurations at the reactive carbon. As you know, you may get an inversion or you may get a retention depending on whether it's the mirror image of the inversion or not. Recall that in an SN2 reaction, the nucleophile does a backside attack and only the inversion is obtained. With an SN1 and you have the alpha carbon, that's not necessarily true. Now here, you have a chiral carbon and you would expect, or you may be thinking that these two, they're in the same ratios, therefore you don't get optical activity. However, that is not the case. When you get this scenario, turns out that the product with the inversion of configuration is going to be that you get in the biggest amount versus the retention of configuration, which will be in the smaller amounts. How far off from 50%? It'll depend on literally it'll depend on the substituents, it'll depend on the nucleophile, but we can expect the majority to have the inversion versus the minority, which will have the retention of configuration. By now, right, we've been discussing substitutions and elimination reactions for a while. One of the major points that I've been trying to get across is that there's a number of factors that affect which products you get when reacting an alkyl halide with a nucleophile and or with a base, whether it's a substrate, the reagent, and the solvent. It should also be clear that in many cases, a mixture of substitution or elimination products will be obtained. Right? So that means that all of these reactions are great and we're able to get what we want, but we're also going to get other things that if you're talking about working in a lab, you are going to have to isolate and purify. It is also possible for a given substrate that only one mechanism will occur. To understand how to use these reactions to transform alkyl halides into a desired compound, one must be able to predict all of the products that will form in a given reaction, as well as the major and minor products. So that's what we call the analysis or retrosynthesis analysis. To successfully predict the product formed in a given reaction, we can follow three-step analysis. Now I will say that this is a great way, it's very systematic, it actually works really well, but if you have a different way of working out these problems, that's perfectly okay as well. There's more than one way to skin this specific cat. So let's look at the process that the author gives us. First step will be to determine the function of the reagent. This is going to be just a solvent, it's going to be a base, it's going to be a nucleophile, etc. Second step will be to analyze the substrate and determine the expected mechanism. And third, consider any relevant regiochemical and stereochemical requirements. So first, remember what kind of reagents promote SN1, SN2, E1, and E2. This table summarizes all of that really well. My advice would be to take some time, especially with this slide, and try to familiarize yourself with the different reagents, the different neutral versus anionic species, larger versus smaller, stronger, weaker, etc., and what each of them does in terms of promoting SN1, SN2, E1, or E2 reactions. Once you determine which mechanisms will be favored by the reagent, we analyze the substrate. Do you have a primary, secondary, or tertiary alkyl halide? And that'll tell you a lot about which mechanisms will be favored to see which mechanism will dominate. And we have actually a table here that kind of summarizes that really well. Again, this is one of those tables that you should take some time to familiarize yourself with them. Third step, after analyzing the reagent and the substrate, you can say which mechanisms will occur. After that, we draw all the possible regio and stereoisomers, then we choose the major using the guidelines we've seen so far. Do we get the side-step product? Do we get the Hoffman product? Etc. For SN2, you will observe a single product, which is the inversion of the configuration at that position where you have the alpha carbon. Again, in the SN2, the nucleophile attacks the alpha position where the leaving group is connected. The nucleophile then replaces the leaving group with inversion of configuration. All of this happens because it's a one-step process, so it's actually pretty easy to predict. For E2, we draw all the possible alkene isomers, only alkenes which result from a beta hydrogen anti-periplanar to the leaving group can form. If you're using a bulky base, then the Hoffman product will be your major product. If you're using a non-bulky base, then the most stable alkene will be your major product. It may be side-step or it may be Hoffman. For SN1 reactions, we draw the carbocation intermediate first. Consider if it will rearrange. If it does, then you do it, right? You perform that rearrangement, and then we proceed with the rest of the reaction, the nucleophile coming in. If not, then we just attach the nucleophile to the carbocation. If it rearranges, draw the resulting carbocation, then attach the nucleophile to it. If a carbon is formed by attack of the nucleophile, then two products are formed. We draw the R and the S. For E1, we draw the carbocation formed from loss of the leaving group. If it will rearrange, we draw the rearranged carbocation. Then we draw all the possible alkene isomers resulting from the elimination of a beta hydrogen. All possible alkene stereoisomers will form. The major product will, of course, be the most stable alkene.